Hi, Johnny. Can you hear me?
Yes, I can.
Yes, I can hear you very well now.
Okay, great.
And are you seeing my presentation? Can you
I
see my slide?
am. Yes.
Are you seeing my presenter's view or the full screen slide?
I'm seeing the full screen.
You are seeing the full screen. Okay, great. So do you want me to start now or wait a few more minutes?
I see we have 20 people on. We can give it a minute while I tell everyone how we'd like to do the questions. I
Sure.
sent a note to the chat, so everyone on should see the chat button flashing, I believe, orange.
Okay.
And we have all the participants muted during this presentation, but feel free to go ahead and write your questions in the chat window. They'll be addressed at the end. Also, at the end of the presentation, if you'd actually like to speak, maybe your question is very long, you can go ahead and unmute yourself, but we're asking that you please don't unmute yourself during the presentation. You can begin whenever you'd like.
Sure. Okay, so then I'll start. Good afternoon, everyone. My name is Oh Sung-won from University of Toronto. I'm an associate professor, and I've been working on this field on hybrid simulation for maybe 10, 15 years, like over 15 years now. Today, I'm going to give a presentation on pseudo-dynamic hybrid simulation. So this presentation is part of the Hybrid Simulation 101 presentation series organized by Multi-hazard Engineering Collaboratory on hybrid simulation, which is led by Professor Shirley Daikai. Today, I'm going to give a high-level overview rather than technical details on pseudo-dynamic hybrid simulation, but you may be able to find a lot of details through papers or the manual or website that I'm going to share today. We do a lot of assessment of structural system in civil engineering, especially for performance-based design or assessment of existing structures like that. And typically, civil engineering structures are of large scale, so we cannot run full-scale experiments except only a few cases. High-rise buildings, long-span bridges, or dams, for example, we will probably be almost never able to run full-scale collapse simulation. That's why we developed numerical model to run structural assessment, and the results of numerical simulation highly depends on how we model it. So depending on the structural elements that we use in the simulation influence the simulation result. In reality, the structural engineering problems in civil engineering involves high nonlinearity. For example, what I'm showing you here is the experimental result of a shear critical column. The red line in the figure is the experimental result, and the black line is the numerical simulation result. Okay. For example, if you look at the red line, it shows degradation of strength, stiffness, and energy dissipation capacity as well. Depending on whether we use fiber section or FE element, we can get quite diverse numerical simulation result that is represented with black line. So depending on how you model it, you may get similar to red line, or you may get quite different from the red line. There are many other nonlinearity problems in civil engineering. The problems of nonlinearity is important because if the system is linear, it is very straightforward to model. In the equation of motion, for example, you just need to define what is stiffness and damping and mass. But if the system is nonlinear, you need to somehow define the hysteretic behavior. Other nonlinear problems in civil engineering is wind and structural interaction. So if there is a flowing wind and structure vibrate, there is an error elasticity of the structure which interact with the wind. Because it is difficult to numerically simulate, people used to run wind tunnel tests. They build a bridge section model of a bridge deck and run wind tunnel tests for cable stayed bridges, or build a building model with terrain and put it in a wind tunnel. Another typical problem of highly nonlinear civil engineering problem is the structure subject to high temperature load. What I'm showing you here is the concrete column that we in fact tested yesterday. And you can see that as temperature increase, the surface of the concrete fall and explode, and the rebar is buckling and heating up. You can see the red line, which is the rebar, and develop buckling. And also you can see the steel column, which is subject to high temperature and start developing local buckling right after we finish the experiment. Modeling of such behavior, that, for example, reinforced concrete structure subject to elevated temperature, is very difficult. So let us try to see, let us see how accurately we can predict the structural responses. And probably many of you have seen this blind prediction contest result. This is the blind prediction contest that was carried out by E-Defense in 2007. They ran experiment, recorded ground motions, that is in fact recorded from the shaking table, provided all the information including material properties, section properties, dimensions, the non-structural components, and everything. So without having much uncertainty in the input to the numerical model, how well you can predict. This is the prediction result. There were 30 participants, and this plot is comparing measured response, which is the red line here, and 3 top predictions by researchers and practicing engineers, which is denoted with the dashed line and solid line. So as you can see here, even though all the information is given as much as they can, the prediction results, top 3 prediction results are still, sometimes it's still pretty good, but sometimes are quite bad. So depending on how we develop numerical model is based on the given information, our prediction can be very bad or close. So there are quite large uncertainties. You can see similar phenomena in the other blind prediction contest. This blind prediction contest was carried out by UC San Diego. And the horizontal axis in this plot is earthquake numbers. So they impose several series of ground motions. And then vertical axis is the maximum horizontal displacement. So as you can see from here, the experimental result, which is the red box, is quite far from the prediction. So in fact, we can tell that even though a lot of information is given, if the structure behaves in the inelastic range due to loading unloading cycles by earthquake load or even by temperature, it is hard to model. That's why we tend to develop experimental specimens as is shown in here. So if we can isolate an element from a system and put it in an experimental setting as is shown here, I'm showing you a column testing machine or shell element tester at the University of Toronto, then impose very well defined boundary conditions such as displacement cycles. Then we can get the result more precisely and you can understand the behavior better. You can do the similar, in a sense, experiments with FE models. If we develop very detailed FE models of connections, then our prediction on the connection behavior will be better than just lumped spring approach. However, this type of modeling approaches takes a lot of time and effort. The idea of hybrid simulation is to take advantage of these detailed models, either numerical or experimental. So if we can model inelastic cyclic behavior, if I use an example of earthquake scenario, inelastic cyclic behavior of components in the lab, and use the detailed model of other components in a FE software and the system model in another FE software, and if we can integrate them all together, then wouldn't it be possible to predict the response of a structure more accurately? So that is the main idea. Hybrid simulation is a useful simulation method when there exists bidirectional interaction between a system and substructural elements. If the interaction is not significant, then in fact there is no point of running hybrid simulation. For example, if there is a building with thousands of structural elements, And if you test only one of them in the lab and integrate it with the rest of the system, then in fact the response of that element may not influence the global response. So there is, to me, in my opinion, there is no point of running hybrid simulation. If that element significantly influences the response, then it is worthwhile. For example, if there is a high-rise building which is supported on a base isolation, and the high-rise building itself remains almost in the elastic range, and base isolation is represented in the lab, then I think this is quite worthwhile experiment. And also, the hybrid simulation is very interesting simulation tool, but it is worthwhile when it is difficult to develop a numerical model of these substructure elements. So in other words, if you can precisely model the behavior of structural elements, then there is no point of running experiment. But if you have a doubt on your numerical modeling strategy, and if you want to see the actual elements behavior and its influence on the system level behavior, then it is worthwhile to run hybrid simulation. As a last point about the hybrid simulation, we need to focus on what we can learn by running hybrid simulation that we cannot learn through conventional component test or purely numerical simulation. Just running hybrid simulation to integrate numerical model and specimens in the lab, it is a very interesting study, but if you cannot learn anything new in terms of structural response or structural performance perspective, then I think it'll stay there just as a interesting work, but not much you will learn from the experiment. So now, in today's presentation, I'm going to give an overview of hybrid simulation. You can see this, in a sense, progress bar. And then I'm going to show you how we implement it at the University of Toronto. So the first section on hybrid simulation is quite general overview. Implementation is somewhat specific to the way we run experiment and simulation at the University of Toronto. And I'm going to give you several examples, either numerical hybrid simulation, which we call it as multi-platform simulation. And then I'm going to repeat this slide summarizing what I have presented today. In the problem of seismic or earthquake analysis or seismic analysis, we are solving this equilibrium equation. At the end, in structural analysis problems, what we are doing is solving an equilibrium equation. It can be either dynamic equilibrium or static equilibrium. In the dynamic equilibrium equation, including earthquake load, we have mass term, damping term, and restoring force term, and applied force term. So for the case of earthquake load, this will be minus m times influence factor times UG double that. So in this equation of motion, we can solve this problem numerically using various time stepping methods, but this restoring force term is difficult to model or present using a numerical model. So if the system behaves in the inelastic range. So the idea of hybrid simulation is that we want to solve this equation of motion numerically using a computer software, and then measure the restoring force from experiment and feed it back to the equation of motion, and we iterate this process. There are various numerical integration schemes regarding how to predict displacement and how to use the reaction force and how to iterate them, not iterate, how to repeat this process. But this is not the scope of presentation today. Today, I'm going to give a high-level overview. If we can model many of the structural system, many parts of the structural system confidently using a numerical model, then what we can do is substructuring. So you can put the most of the structural system in the analytical or numerical substructure, and then put the experimental specimen in the experimental substructure. We ensure compatibility at the connection, at the interface, by imposing identical displacement vector that is predicted from the numerical integration scheme. And then restoring force vector is added from the numerical model and experimental specimen. And then we feed this restoring force vector back to the integration scheme. So I'm showing this triangular shape to represent that part of this term, or the restoring force term, is represented experimentally. This type of problem doesn't need to be only for the restoring force term. For the case of the wind-bridge interaction, what they typically do is to develop a section model of a bridge in a wind tunnel, and they impose wind pressure, the flowing wind. Then there is interaction between this bridge deck's response with the wind. So the wind force, external force, is a function of displacement of the bridge deck and velocity of the bridge deck. Because there is an interaction between the applied wind flow with the displacement and velocity of the system, we cannot predefine this right-hand side term. So this term, in fact, can be represented experimentally in the lab because this is difficult to model numerically, and part of the system's mass is represented physically. So part of this vector, the force vector, is represented physically, and we can run the hybrid simulation as well. This is one of the topics that my students are working on nowadays. The idea of running hybrid simulation, another application is the structural interaction due to fire. So let us assume that this structural system is subjected to fire. Then we are solving this problem. This is a static problem where the restoring force vector is a function of imposed displacement and temperature and applied force. In this case, the applied force is the gravity load, and temperature changes over time. Let us assume that we satisfy equilibrium and temperature changes gradually. Then what happens is that this equilibrium between restoring force and external force will not be satisfied. So we need to update displacement such that the equilibrium can be ensured. So in that sense, we are solving nonlinear solution scheme to ensure the equilibrium between restoring force and applied force. And in the solution scheme of the solution scheme predict target displacement, and you can run the experiment. So as I explained briefly in the 3 to 4 slides earlier, in hybrid simulation, we essentially solve equilibrium equations, either static or dynamic. Hybrid simulation doesn't need to be only earthquake engineering problem or dynamic problem. It can be static problem as well. As long as there are parts of the equilibrium equation that is difficult to model numerically, we can model experimentally. So in the seismic application, for example, this restoring force vector is difficult to model fully numerically. So part of the structure can be modeled experimentally. In the temperature load, in similar, in wind load case, we are in fact defining external force experimentally rather than the restoring force. So terms that we understand well are represented numerically, and the rest can be modeled experimentally. It doesn't need to be restoring force only. It can be either restoring force or the external force as well. Hybrid simulation, there are mainly 2 types of hybrid simulations, as you may heard from Professor Oh's presentation earlier. So one of them is the real-time hybrid simulation. Some physical represented terms. When I say represented terms, it does not mean this restoring force only, or it can be the applied force as well. So some physically represented terms in the equilibrium equations require realistic rate of loading, because physical elastic temper or physical temper, as shown here, depends on the velocity impulse or acceleration that impulse. Some elements, tuned liquid damper, tuned mass damper, gyro mass or inertial mass damper, requires accurate or acceleration. Wind flow interacting with deformed geometry of structure is a function of the vibration frequency. So how fast the structure moves with respect to the wind. So it requires also real-time simulation. And heat conduction, even though it is a slow process, you cannot control heat conduction in a stepwise manner. So it needs to be done in a real time. So these type of problems require real-time hybrid simulation. Some of them are dynamic, like all the rest except the heat flow case, or some of them is static, or rather pseudo-dynamic problems. It's a slow process, but in all of these tests, the experiment should be done in the real rate of loading or real rate of temperature increase in the case of the fire problem. There are advantages of real-time simulation. Advantage is that there is a realistic loading rate. So if the elements depend on the rate of loading, then it is applicable. So in fact, it is applicable to all structural elements, regardless of whether the element is rate dependent or rate independent. Even the rate independent elements, such as steel beam column connections, you can still use real-time hybrid simulation. There are many challenges in real-time hybrid simulation as well. One of the main challenges that has been a research topic for many years by various researchers is the actuator delay compensation. So there's a negative effect of the delay of actuators. So they developed the actuator controller to compensate the delay. And also for the dynamic problem, it requires dynamic actuator, which is somewhat slightly different from the actuators that are used mainly for static tests. Numerical models needs to be simplified if we want to do real-time simulation. Not only the experiment, but also analysis should be completed within a given time step. For example, if we run a time integration scheme with 0.01 second of numerical integration time step, then all the analysis needs to be done within 0.01 second, and experiment needs to be done within 0.01 second, and the response of these two analysis or experiment need to be integrated, which is a little bit challenging for nonlinear problems. Nonlinear problems is not impossible to solve through real-time hybrid simulation, but if the size of the problem becomes bigger, then the computational time becomes a bottleneck. And also, because the experiment needs to be done in real time, it is generally difficult to correct issues in boundary conditions during an experiment. If you have done real large-scale structural testing in a lab, you may know this issue. If you impose deformation to a specimen, sometimes the support slips, which should be avoided, but sometimes it's not avoidable. Sometimes the reaction frame or reaction wall deforms slightly in the elastic range. So what we typically do is to measure deformation of the specimen directly. So the stroke of the actuator is not representative deformation of the specimen. So somehow we need to correct all these issues during the test. Many other physically represented terms in the equilibrium equation that I explained earlier is rate independent. In fact, most of the civil engineering structural elements made of reinforced concrete, steel or wood or masonry, for example, are rate independent. So their behavior is mainly a function of displacement history rather than velocity or acceleration. There is some studies where they have rate dependency issue of these elements, but to me, I feel that for the case of earthquake engineering problems, the rate dependent behavior of these elements is not so significant. So for this kind of problems, we can use pseudo-dynamic hybrid simulation. The advantage of pseudo-dynamic hybrid simulation is that we can use sophisticated and highly nonlinear numerical model for the rest of the system. Because the time scale is expanded, we do not need to finish the numerical integration within a given time step, such as 0.01 second. We can run many iterations in the numerical model, and then we can move on to the next step. And also, because this is not a dynamic problem, for the case of static problem, and in fact, this is not a dynamic problem, so we do not need the dynamic actuator. Most conventional hydraulic actuator and controls can be used. And I'm going to explain this a little bit further later on when I explain the communication. Delay compensation is not required because delay is not an issue. And there is a time to correct any boundary condition issues during the test, such as elastic deformation, slip, and gap in the experimental setup. We try to avoid these during the experimental setup when we build experimental setup, but we cannot perfectly eliminate all of this. So we need to somehow correct this during the experiment. The challenges of this method is that we cannot run the test with a damper, such as viscoelastic damper, which is a rate dependent. So this method, pseudo-dynamic hybrid simulation method, is applicable only to rate independent elements. So basically, hybrid simulation is a substructuring technique. So the restoring force vector is sometimes displacement, velocity, or acceleration dependent, depending on the type of the problem. But as long as you can substructure it and solve this equation of motion or equilibrium equation, then you can run hybrid simulation. Generally, what the required components in hybrid simulations are as below. So we need one main integration module. For the dynamic problem, the integration module solves dynamic time integration schemes such as MECHS method or alpha-OS method. For static problem, the main integration module solves the nonlinear solution scheme. Dynamic problem can be nonlinear as well. We typically use explicit scheme, however, to avoid iteration through that we normally do in the implicit scheme. We typically use non-iterative solution method even for the nonlinear solution scheme, because especially for the real-time simulation. Because if we need to do certain number of iterations and the number of iterations is different at every time step, then it is difficult to maintain the timing. Another essential component to run hybrid simulation is communication. At the end, the hybrid simulation is, in a sense, very similar to the typical finite element analysis in a sense that some of the restoring force factor is coming from one element, another restoring force factor is coming from another element, which is physical element now, and we are just assembling them to form the large restoring force factor. So the problem is how to send predicted displacement to actuator controller, how to read the force, and how to feed it back to the FE analysis software or numerical integration scheme or numerical integration module. So communication becomes one of the major component in implementing hybrid simulation. So once you send predicted displacement to actuator controller, then the next question is how to impose the predicted displacements accurately to the specimen. So that is another major requirement. And in real-time simulation for dynamic problems, delay compensation becomes a critical step that you need to implement. So now, if now I'm going to show you how we implement and run experiment at the University of Toronto. So the UI-Synco is the program that I wrote when I was a student, which runs only time integration scheme. It doesn't have any numerical model or numerical elements. It just runs alpha-OS scheme or any other time integration scheme. The restoring forces are all taken from either experimental substructure modules or numerical substructure modules. So in this slide, you can see integration module, which runs main program. And the left-hand side is either numerical substructure module or experimental substructure module. And we have developed a program called the Cyrus, mainly to integrate various vector programs, which are specialized for the reinforced concrete structures. And then sometimes we use OpenSys, SP or MP, Abacus, and S-Frame, etc. So integration module can be anything. So if you have your own program, you can use it as a main program for hybrid simulation. As long as you can send data to substructure element, either in the numerical element or physical element, and get the data back to the your software, then you can run hybrid simulation. So the main component of hybrid simulation in that sense is communication. As long as we can send and receive data between various softwares, then we can mix and match various numerical or physical elements and develop a system level model. We typically use one of these, well, it can be any others, but one integration module and one or more substructure modules in hybrid simulation. To facilitate the hybrid simulation, what we have developed is the standardized way of exchanging data between different software. So by standardizing this in our group, we can literally mix and match many different softwares in this slide. So we developed the data exchange format and communication protocol such that we do not need to re-implement whenever we run an experiment. We can use just a library and connect to any one of these and send and receive data. So this is very flexible, it has a very flexible structure. And we built a library file which you can call and connect and receive data. Send and receive data. This library file has been compiled as dynamic link library DLL file or the out file for the Unix system. So it can be called from C++, Fortran, LabVIEW, and MATLAB. So if you want, you can build your own substructure model in MATLAB or even in OpenSys and connect it to other programs. Another main component in running hybrid simulation with physical specimen is communication between the actuator controller and the one of these main integration modules. Typical actuator controllers do not have a functionality to receive and send data through network, so digital communication. So what we have done is this. We developed a program called NICON, which we call it as Network Interface for Controllers. So if I give a short review of what I have presented in terms of hybrid simulation. For dynamic problem, we have numerical integration scheme and numerical substructure module. These two components, the numerical integration scheme and substructure models, are typically modeled in a single software. In the UI, I think it is a little bit different because this is separated. But in Abacus, OpenSys, or any other analysis tool, you are solving this problem, dynamic problem, all together. If you want to represent one of the column in the lab, we put it as a specimen in the lab, and these actuators are controlled with actuator controller, and it has their own loop, PID loop, to control stroke of the actuators. We need to send this displacement command to somehow to the controller. What we typically do in our lab is that we send the data from this component to the interface program, NICON, through network, TCP/IP network. So you can just plug in through internet and then send data to here. And then the communication between this program to controller is carried out by imposing analog voltage signals and reading analog voltage output signals from the controller. In between, there are several processes that we implemented. In fact, in this perspective, this is same as the 3-loop configuration that Professor O presented in the earlier presentation. So even in the real-time hybrid simulation, there is a one loop showing the PID loop for the control of actuator, another loop which is for the delay compensation, and the third loop is for the solving dynamic integration scheme and send and receive data. So this is a 3-loop structure. In pseudo-dynamic hybrid simulation, this part, the component number 3, is not running at the full speed in real time, but it does a lot of checks and the corrections for the boundary conditions. So in terms of communication, as I just explained, we use TCP/IP network and analog voltage I/O. So why we are using analog voltage I/O? There are some reasons. Between the hardware controllers, in this case hydraulic actuator controls, between these hardware controllers and the software, there are various ways of running communication. One is ScramNet. ScramNet is quite common with MTS actuators. But in other fields of robotics and other factory automation problems, they communicate with the controller through Modbus TCP or Ethernet. So there are digital ways of exchanging data. As far as I know, most of the hydraulic actuators, if you have an actuator in your lab and a controller in your lab, there is a ways of running analog communication. So in a sense, imposing displacement command through voltage signal, and there is a way to output the result. So analog communication is very traditional way of imposing displacement and receiving outputting the measured responses in most of hydraulic actuators. In the past, I have used MTS controller, short Western controllers from Instron and Samyang, etc., to run pseudo-dynamic hybrid simulation using analog voltage I/O signal. That is the reason why we use the analog I/O to run communication between numerical model and actuator controller. For sure, there is a disadvantage of voltage I/O because of the inherent noise coming from the analog signals. But as long as you insulate them properly and ground them properly, it is fine. I have seen many other research groups using analog voltage I/O to run real-time hybrid simulations as well. There are several other functionalities that we need to run hybrid simulation, and what the interface program takes care of is the coordinate transformation. For example, in the FE software, if you analyze a frame element that is 12 DOFs per element, so 6 DOF per node, we need to align them to a local coordinate system, because the rigid body mode does not influence the restoring force of the element. So we take out all the rigid body mode and just use the deformation modes. And because this local coordinate system may not be aligned with the experimental setups coordinate system, we need to align it with the experimental setups coordinate system. And then experimental setups displacement vectors will be different from the individual actuator's stroke. So we need to convert the displacement in the experimental setups coordinate system back to the actuator's strokes. And once we impose deformation, we read forces from the load cells and convert these load cell readings all the way back to here. So this is the one process that we need to have in the interface program. There are several other features such as ramp generation. It can be ramp and hold, or it can be continuous, or safety checks, etc. So in case the command is too large that may damage the specimen or equipment, we need to control that. So these are main features of the interface program, which has been generalized for various task configurations in civil engineering problems, such as shown here or in the next slide. So you can do multi-DOF control or many single DOF control. So essentially, if you want to run hybrid simulation, pseudo-dynamic hybrid simulation in your lab, what you need is one of these software, or it can be your own program as well, MATLAB. And then what you need is is a way to send and receive data. So to the actuator controller. To receive and send data, we can use network communication using the UTCM framework. And then to impose received displacement to the actuator controller, we use NICON, which is written in LabVIEW, and it interfaces with various hardware, data acquisition hardware from National Instrument. For the purpose of training, because in the very beginning it's hard to start, and also it is a little bit dangerous because you don't want to damage specimen or equipment. So what we have done in our group is that we built a controller and actuator and specimen which mimic the behavior of a hydraulic system. It's not a high power. It doesn't have high force capacity. It's not a real time. It is but the position of this element is controlled through a stepper motor, through the signal, analog signal that we can read from NICON. So we can do this as if we run pseudo-dynamic hybrid simulation in the lab. Once all this process is successful, we just remove this and plug the analog communication wires to the hydraulic actuator controllers. Then you can run hybrid simulation. We have developed a system. Soon we will distribute how to build this. This doesn't cost much and made it quite easy to build. And in fact, I could build it myself, so I think you can build it yourself as well. This is very easy to build using Arduino controllers. So I'll show you several application examples. For the sake of time, I'm going to go through somewhat quickly. One of the application example is using UI Synchro, OpenSys, and generic actuator controller, where we tested self-centering energy dissipating brace, which was invented by my colleague, Professor Konstantin Christopoulos. So the building is a 6-story building, and the brace is an energy dissipating brace. So it mainly consists of 2 steel tubes confined with the tendon. So both in compression and tension, it behaves linear elastically. The tendon behaves in the linear elastic range, and it comes back to the original configuration after the imposing large inelastic cycles of loading. So we ran pseudo-dynamic simulation. The specimen is in the lab, and data exchange between the specimen and the OpenSys model was carried out through internet network and analog voltage I/O, and you can see the lower connection, upper connection, and hysteretic behaviors, etc. I'm not going to go through details about the test results for the sake of time, but this is the way we ran hybrid simulation. So you can see the overall configuration of the experiment. Another example is the integration of OpenSys with generic actuator controller. This is not using, as I told you before, using scramble. You just impose voltage signals from NICON to the actuator controller. So in this test, we use the hardware called UT10 simulator, with which we can test up to 10 actually loaded elements simultaneously. Because the actually loaded elements is typically very stiff and there is problems of elastic deformation, what we do is that we measure the deformation of the specimen directly from the specimen and feed this information, this data back to NICON and correct commands. There is some error correction loop between NICON, MTS controller, and the specimen. And we use OpenSys to run main integration module, the medical integration module. So we ran experiment for 6-story building, which is a 5-story building, which is designed for the Los Angeles. And this is showing the experimental specimen, which represent the core of BLB. And this is the experimental result. So you can see that there is a slight difference between the medical result, which is hybrid simulation, which is black line, and numerical result, which is a red line. That is, this slight difference was resulting from the unloading during the loading phase. So if there is slight unloading when there is transition between elastic to inelastic, somehow numerical model shows a sharper transition than the experimental result, which resulted in this difference. So again, this shows that by running hybrid simulation, we can identify potential issues with the numerical model as well. We have done 3 element tests, so 3 BLB elements tested simultaneously. And recently, using the same test configuration, we have ran hybrid simulation of 4 buckling braces simultaneously. So you can see that there are 4 braces representing 1, 2, 3, 4 elements in a building. And hysteretic behavior, buckling hysteretic behavior is quite complicated, but they are quite nicely represented physically in the lab. And you can see they look like a dancing back and forth. And this represents the braces in the lab, in the numerical model. Another application example is the numerical hybrid simulation. As I told you before, this type of simulation technique doesn't need to involve experimental specimens always. If you have a better tool to run or to represent a component of a system, then you can run numerical simulation as if you are running physical hybrid simulation. For example, in this case, we modeled the 3-story building where the beam column connection is the critical area. And this beam column connection failure is very difficult to model using frame elements unless you use calibrated lump springs. So for this study, what we did was that we modeled beam column connections using Vector 2. And Vector 2 is a specialized analysis tool for reinforced concrete structures based on the modified compression field theory that has been developed by Professor Collins and Professor Vecchio at our institution. So by integrating Vector 2 and OpenSys, we could see the crack distribution and shear failure of the connections, which is similar to what we can observe from Vector 2 output. So we ran multi-platform simulation. Another example is the integration of a UI Synchro with the NICON and actuator controller and OpenSys. Because this communication layer is done through internet network, we can separate the many programs in many institutions. Many substructures in many institutions. So in this demonstration experiment, we analyzed or simulated a bridge where one of the bridge bearings was tested at the University of Patras in Greece, and various other components were placed in Canada, in the US, Italy, and Greece. So we could run multi-site distributed simulation using the method that we have used, that we have developed so far. So if you take this approach, you can take advantage of various unique experimental facilities around the world. Another example is the Abacus and hardware, the actuator controller. Abacus doesn't have functionality to run communication, so we developed user-defined element, which is an element for Abacus, but it runs communication through network. So these user-defined elements then predict displacement to the program NICON that I explained earlier, and it communicates with the generic actuator controller. In this example, I'm showing you 4-story building where the 4-story column is modeled in the lab in furnace. So this is a furnace where we can burn gas and increase temperature. And the column is red, not because it is painted in red, but it's glowing from heat. So the temperature load is modeled in the lab, and the interaction between the structural system and the specimen was done through hybrid simulation by controlling actuator at the bottom of the experimental setup. So they can impose temperature and deformation simultaneously. So you can see that from here, you can see that while you are imposing gravity load, the column shrink a little bit because of compression, and the load increase, and eventually column expand when we heat. As temperature increases further and further and further, the material property changes from elastic to inelastic, and strength of the column decrease, so it starts yielding, even though column is heating and keep heating, and the force is decreasing due to the yielding and change of the material properties. And then once we start cooling, it goes all the way through this way. So you can see the collapse sequence of the entire system through hybrid simulation, and also you can impose more realistic boundary condition than conventional constant load the fire test. Another example is OpenSys and vector. I noticed that some of you registered audiences have a background in geotechnical engineering. So this one is, in fact, geotechnical engineering problem. We modeled the Daikai station that collapsed during the 1994 Kobe earthquake, where the soil was modeled in OpenSys, and the tunnel itself was modeled in vector. So vector program, as I mentioned earlier, is good for modeling reinforced concrete structure. So by modeling the tunnel using most representative numerical model, while the rest of the soil domain is modeled in OpenSys, we could see clear interaction between the soil domain and the structure, and failure sequence as well. So if we use single software, it is somewhat challenging because not a single software includes all the features that we need for research or engineering practice. So hybrid simulation, pseudo-dynamic hybrid simulation, doesn't need to involve experiment. If you want, or if you find it is feasible, you can make a detailed model in other software and connect it to other system-level software and run the interactive simulation. So I just presented about the hybrid simulation. Hybrid simulation method is a useful tool for analysis of structural system, where part of the structure can be better represented with a physical specimen or other soft-skilled numerical models. So when I say part of the structure, in fact, I should say some terms in the equilibrium equations, because sometimes we define the load in physically. Okay? So if you can model some of them more realistically, then you can get more realistic, more accurate prediction. Hybrid simulation, as I explained earlier, is a useful tool when there is significant bidirectional interaction. If there is only unidirectional interaction where the system response governs the elemental level response, then there is no point of running hybrid simulation. If element behavior influences the system behavior and the system's behavior influences back the element's boundary condition, then it is worthwhile to run hybrid simulation. Unlike real-time hybrid simulation, pseudo-dynamic hybrid simulation has some advantages because it can involve soft-skilled numerical model, especially because it does not require completing analysis in a very short time interval. And also, we can use conventional hydraulic actuator control system. So even if the hydraulic actuator control system is decades old, as long as it has analog input and output, then you can run hybrid simulation. We have developed a website and manual to run hybrid simulation as the way we do at the University of Toronto. And some of the information is available at the website. And if you need any further information, feel free to send me an email. My email is shown in the beginning of the presentation. Thanks for your attention, and I'd like to answer your questions. If you have any questions, I can answer your questions right now if you type your questions. But what I'm seeing here is that I do not see any questions online. So if you have any questions, you can either type it now, or you can unmute and then you can ask questions online. Okay.
Question was just posted. Yes.
Yes, I just one question. How was the interaction between Vector2 and OpenSys was modeled? That is the question. So how was the interaction was modeled? In a sense, that is done in the exactly same way that I explained. So let me first show this slide. So OpenSys is running in a desktop. We developed substructure element which runs communication through the standardized data exchange format and protocol. So OpenSys, the system model includes substructure element. Substructure element communicate with the Vector2, and we included the same communication protocol in the vector programs as well. So OpenSys run one step of analysis, predict displacement, send displacement to Vector2. Then what Vector2 does is run analysis by imposing boundary condition at this boundary, and then return restoring force back to OpenSys, and we continue. So Vector2 has been used in this case, is used as if it's a physical specimen in the lab. So that was the way we ran OpenSys Vector2 integration, and that was the way they were interacting. Did I answer your question? If you have any other questions, feel free to type as well. How can apply to Athena? So that is the question. I haven't tried to use Athena. If Athena, as far as I understand, Athena is the program for reinforced concrete analysis. If Athena has a functionality to impose displacement boundary condition or update displacement boundary condition at every analysis step, then in fact it is possible to write a program to redefine displacement boundary condition at every time step, impose it to Athena, and get the analysis result from Athena and put it back to the system level model. I think it is possible. There is one way is to write a REPRA program. Another way is contacting Athena. If the developer of Athena in the program which can communicate through a network, then I think it is also possible to involve Athena as well. Maybe the developer of Athena might be interested in having the communication scheme. In fact, I didn't present it as an example, but this program called S-Frame. S-Frame is similar to SAP 2000 or ETAPS. It has been used for design and analysis of structure. We worked with the company such that a designer can model the designer building like this, and then click the main element that behave in the inelastic range, and send data back and forth with a Vector2 as well. So then designer or engineer can use their own numerical model that they use for the design and analysis and include nonlinear elements quite easily by running sort of multi-platform simulation. So if you contact the developer, then they may collaborate with you because it'll benefit the company and engineers as well. And there are several other questions. Let me try to answer another question. Let me see now. So after the question about Tanner, the next question is, can you explain more about the maximum test rate for stiff specimen? I call this quasi-static hybrid testing. Okay. The question is the maximum test rate for stiff specimen. Okay. For pseudo-dynamic testing, the test rate doesn't really matter. For real-time testing, test rate, the rate of testing should be in real time. And for stiff specimen, even for the pseudodynamic testing, even if the test rate is not an important, testing a stiff specimen is already challenging because of the boundary condition. So when I say boundary condition, what I mean is this. In hybrid simulation, in most of the hybrid simulation, we use displacement control. I have seen papers on mixed type simulation where force and displacement is mixed. But most of hybrid simulation is based on displacement control. When you say displacement control, we want to control deformation of the specimen, not the deformation of the actuator stroke only. So if the boundary condition is perfectly rigid, so supports are perfectly rigid, then the actuator stroke is same as deformation of the specimen. However, if you use stiff specimen, then the reaction slab or reaction column or reaction floor or reaction wall may deform slightly. So that slight deformation may appear as the flexibility of the specimen. So you need to instrument stiff specimen with high precision displacement transducer and use it as a feedback directly to the actuator controller, or use it as a feedback to the interface program, which is in our case, which we call it NICON, to correct the error in the boundary condition. So there is a challenging stiff specimen, but for pseudodynamic testing, there is no issue of the test rate for stiff specimen. So now the other question now is this. I'm interested in wind applications. Do you think pseudodynamic hybrid testing can be used for wind? To me, I think it will be difficult to use pseudodynamic testing. Well, in my group, we are using real-time testing now. We are developing on hardware and experimental setup that will be in a wind tunnel, and it'll move in real time. It'll be difficult to use pseudodynamic testing because the interaction between the wind and structure is rate dependent. So conventionally, for the bridge deck application, for example, they define the interaction between wind and bridge deck using a linearized term called floater derivatives. So floater derivatives is a relationship between the frequency of vibration and the applied load, where the term frequency involves some rate. So high frequency means high velocity. So it is difficult to use pseudodynamic testing in wind tunnel test. That is my opinion. There might be a way, but based upon up to the knowledge that I have, I think it's a little bit challenging. Another question is, one of the problems we face in wind tunnel is how to define exact same wind load that the elements see in the lab as a structure in the numerical model. So in our research group, we are not modeling wind pressure numerically. All wind load and interaction between wind and specimen will be represented physically. And damping in a numerical model. So this is not a problem that we are facing. I'm not exactly sure how to define wind load. I have seen papers in wind hybrid simulation. So there are some papers from Japanese research group where they, in the first paper, they used load cells to get influence of wind pressure. In the second paper, they applied many pressure transducers and integrate the readings from the pressure transducer and impose it in the numerical model. So I think that is probably the answer that you are seeking for. There are two papers that you may want to find from Japanese researchers. And let me see other questions. I think that's all questions that I have. Do you have any other questions? If you have questions, you can type now. I can wait. Or you can unmute and you can talk. Okay. If you do not have any other questions, I will complete my presentation here. I'll finish my presentation here. And if you have any other questions, feel free to send me an email that I showed you earlier in the slide. Thank you.
Thank you, everyone, for attending.